Thanks. My name is Rick Houlihan. I run the NoSQL Black Belt team for AWS, which means I do a lot of DynamoDB. But I work with all NoSQL technologies. I spent a couple years at MongoDB. I've been working with NoSQL technology for about 10 years. And I've done probably close to 1,000 NoSQL apps, hundreds at least, probably close to 1,000 at this point. And really what it comes down to is, it's one of the things I've learned in all the time that I've worked with NoSQL technologies is there's no such thing as a non-relational database. So when people tell you that NoSQL is non-relational, then they probably don't really understand what they're talking about, and we're going to get into that as we talk through this. So today's session we'll talk a little bit about, I like to kind of go through a brief history of database technology, and the reason why I do this is kind of set the stage for why are we even looking at NoSQL technology today? Why is this important for us to know how to use this, and what are the reasons and the drivers behind the invention of this new database technology? We'll get into a brief overview of DynamoDB. How many people have used Dynamo? Okay, so quite a few. That's good. So you guys will know the basics. I'm going to spend a little bit on that structures and fundamentals, but not a lot. I'm going to go deep into the kind of the data modeling. You know, how do you take relational data and move it into a denormalized data store like Dynamo or other NoSQL databases? And that's really what the meat of the conversation today will be, is about data modeling and design patterns for NoSQL. And then I'll talk at the end a little bit about the kind of serverless ecosystem and how DynamoDB plays in that ecosystem and go from there. So in the beginning, when you look at database technology, over the years we've had a series of what I call peaks and valleys in data pressure. And data pressure is the ability of the system to process the amount of data that I'm asking it to process in a reasonable cost or a reasonable time. And when I cannot do one of those things, that's a technology trigger. And that's when we're going to invent things. And we've invented many things over the years. The first database we had was a really good one, right? It's the one between our ears. We're all born with it. Highly available. When my eyes are open, it's online. But it's a single user system, right? Questionable durability of zero fault tolerance. So very quickly we learned that we had to do something else. And so we started writing things down. And we invented a system of ledger accounting. And that was the first mechanism that we used to store structured data. It really was the first database. And ledger accounting ran public and private sector applications for years, many years, millennia, until the 1880 US Census came along, and a guy named Herman Hollerith was tasked with processing all of that data. And if you're familiar with the US Census, it runs every 10 years, and it took Mr. Hollerith and his team about 8 of those 10 years to process the 1880 US Census data. So he realized in 1890 something was going to have to change because we weren't going to be able to get it done. And he invented the machine-readable punch card and the punch card sorting machine. And the era of modern data processing was born. So very rapidly we started to develop a new sets of applications to consume this data, new mechanisms to store the data, paper tape, magnetic tape, distributed file systems, random access storage, and eventually we landed on a neat technology called the relational database. And the reason we built the relational database is very simple. It's because storage was expensive. Extremely expensive. As a matter of fact, in 1983, I was walking through Macworld in Moscone Center, San Francisco, and in the middle of the conference room, there was this truck transmission. I said, wow, why is this giant truck transmission in the middle of this technology conference? And I went over there, it wasn't a truck transmission, it was a cross-sectioned hard drive, and it was actually a data recovery service, and it was from 1974, and it had a little sticker on it that said 4 megabytes and an MSRP of $250,000. That's US dollars, so a lot more in Australian dollars. But obviously, it was expensive. And so there was a reason we invented the relational database, was to normalize the data and to deduplicate the data. In essence, maximize the most expensive resource in the data center, which was the disk. Now fast forward 30 or 40 years and the opposite is true. The CPU is the most expensive resource in the data center, and the disk is cheap. I pay pennies for gigabytes of storage today, but I pay for CPU seconds. So why would I use a technology that's built to optimize the least expensive resource in the data center? Because that's what the relational database is. So now, when we start to look at the cost of dealing with big data, we've invented a new set of technologies to do that, and it's NoSQL and the distributed database. And so we'll get into how that actually works. But the first thing I like to talk about here is when you learn new technologies. And learning new technologies is about learning new ways to do things. And when you don't learn new ways to do things and you try to learn and use those new technologies anyways, you fail. And that's what this is about. So if you look at the chart on the bottom here, this is the technology adoption curve. We're very familiar with this. In the beginning, there's some technology trigger. Everyone's having a problem. People invent solutions. Some people have success. Other people run to use those solutions and deploy these new technologies, and they have a miserable experience. Okay? And the reason why is because they're trying to use the new technology the same way they use the old technology. And this is the biggest mistake I see with teams struggling to use NoSQL technology today, is they're building these wonderfully normalized data models, multiple tables, they have parent-child relationships, because we think this way as developers, right? 30 years ago, I used to interview developers and I would ask them, what's an inner join, right? Do you know how to normalize this data model? I don't ask a developer those questions anymore today because relational technology is way out in the laggards section. If you don't know what an inner join is today, then you've been living in a cave for 30 years and I don't know how to help you, right? But if you don't understand NoSQL technology, well, that's understandable because NoSQL is in that technology gap, right? People don't know how to use this stuff. It's new. Most of us haven't had to solve the problems that it was invented for, so we haven't had to learn how to use it right. So bottom line is, if you want to have good experience with new technology, and NoSQL is one of those technologies, learn how to use it before you deploy it, and you'll have a much better experience. So when do I use it? And it's not for everything. So a lot of people will tell you NoSQL is going to replace the relational database. That is not true. As a matter of fact, the relational database has a really good place today, and that's in that kind of OLAP style workload, right? Online or analytics, business intelligence, a reporting application, somewhere. So if I don't understand the access patterns, I don't know the questions people are going to ask, then a relational database is a really good choice. But NoSQL databases use denormalized data models, and what that really means is I'm going to tune the data structure to support the access pattern. It will be specifically built to target a specific application, okay? And so what that really means is that for transactional applications, OLTP applications, where every time the user hits the button, the same thing happens, right? Shopping carts, business processes, common business processes. This is the type of application where NoSQL excels because I can tune that model specifically to the access pattern and achieve extremely efficient performance, from the system. So lucky for us, that's 90% of business applications are designed to support a very specific and common business process. So OLTP applications are really, really good for NoSQL. So you look at DynamoDB, probably the biggest value point for Dynamo is it's a fully managed system. How many people have run a scaled out NoSQL database? Like I'm talking more than 15 or 20 nodes. Not many, right? When you start to run the number of nodes out, beyond a reasonable size, it becomes very difficult. So a lot of the customers that I talk to are the ones that have scaled out their NoSQL databases so much that they're feeling the pain, the operational pain of managing that. And so the biggest reason that they're coming and talking to me about DynamoDB is they want to get away from that, right? Not many people are in the business of running a distributed database. Right? And it's a lot of work to do that. So DynamoDB does all of that for you. It is a document or key value store. It's really a wide column key value store that supports a document attribute type. And we'll talk a little bit about what that means when we get into the data modeling. But one of the best value features of it is that it is designed for fast and consistent performance at any scale. Now, all NoSQL databases share this common characteristic, and we'll explain why that is. But DynamoDB is built out and proven to operate at a scale that goes beyond pretty much any other NoSQL platform I've ever seen. The fastest DynamoDB table we have today is operating at about 5 million writes per second. So I have never seen a Cassandra cluster or a MongoDB cluster scaled out to that level of performance. And we have many, many, many tables operating. As a matter of fact, the DynamoDB service backplane in 2017, Prime Day, peaked out at 54.5 million transactions per second. So it's a pretty amazingly performant solution. Fine-grained access control. With IAM users, you can specify item-level access control, permissions at the attribute level on those items or the table level, and it is a backplane service. It's what we call a tier 0 service. We don't have many of those. Tier 0 service means that there's a region, what we call a region build process. When an AWS region goes live, DynamoDB is the first service to deploy because every other service is built on it. So if you want to talk about reliability, it's the linchpin of AWS region builds. Every other service we have is built on top of it, so it has to be a rock-solid, reliable service. As a matter of fact, there's now an SLA out for DynamoDB. It's 4 nines on a single region deployment. It's 5 nines if you're using global tables. So if anyone has been in the business of operating a 5.9 reliability service, you know what kind of infrastructure investment you have to make to deliver that level of performance guarantee, and DynamoDB is doing that every day. So DynamoDB has tables, like all NoSQL databases have some flavor. We call them tables, MongoDB calls them collections, Cassandra calls them key spaces, but they're all the same. It's a place you stick stuff. You push things into the table. Items on the table have attributes. Not all the items have to have the same attributes. This is kind of schemaless, I guess you'd say. But there is one required attribute. In all NoSQL databases, there's a unique identifier, right? I have to know how to uniquely identify the item. In DynamoDB, that's called a partition key. So we will have to provide a partition key attribute to be able to look the items up. I can also provide an optional sort key. And what this allows me to do now is create groups of items within partitions. So you can think of the partition key as kind of what identifies the folder, and the sort key identifies the order of those items within the folder. And I can actually execute complex range conditions against those sort key values to pull back selective results. So think if I had a partition key, which was a customer ID, and I had a sort key, which was a order date, I could say, give me all the orders for this customer in the last 24 hours by saying select star from table where customer ID equals X, and the sort key is greater than 24 hours ago. And give me the orders in the last 24 hours for a given customer. So this is generally what we're going to do with DynamoDB or with any NoSQL database. We're going to use this schema to kind of support specific access patterns. And then we're going to use indexes to support additional access patterns. And we'll talk a little bit about how we'll do that when we get into the modeling. So when you look at scaling NoSQL database, it's about horizontally distributing the load. And the way we do that in NoSQL is we take that partition key value, or that unique ID. In MongoDB, it's underbar ID. As a matter of fact, I actually use the shard key to distribute the items. And Cassandra also uses partition keys. But what we're doing is we're trying to create some arbitrary key space. We're going to use that partition key to create an unordered hash index and lay these items out across that key space. And when I need to scale the system, what I'm going to end up doing is chopping up that key space and say, you, node, you're responsible for this chunk of the key space, and so on and so forth. So when you give me a query in a NoSQL system, you're going to give me some sort of equality condition on that shard key or that partition key that's going to tell me exactly where to go, which node in my array do I go to query that data. So this is one of the reasons why NoSQL databases are fast and consistent at any scale, because the query is going to direct me exactly to the correct storage node, no matter how many storage nodes, no matter how much data is stored in the system. Again, when I add that sort key, now what I'm doing is I'm aligning these items within the partitions and giving me the ability to do very quick lookups of selective result sets that match my query conditions. So this is kind of the crux of NoSQL development, is to say I'm going to design a table schema that is going to support my access pattern very specifically. And I will rearrange this data depending on the nature of that access pattern using indexes. So we'll talk a little bit about how we're going to do that. In DynamoDB, partitions are three-way replicated by default. All regions have 3 availability zones, whether you see them or not. In some regions, you might look at the console, it might show you only 1 or 2 AZs. Yeah, for DynamoDB, we need 3, so there will be 3. 1 might not be available to you as a user to deploy instances or to create VPCs, but there will be 3 AZs. When you write to DynamoDB, we will acknowledge the write when it has replicated to at least one of the secondary nodes. So you're always going to write to the primary. And then it's going to replicate, and once it's replicated to one of those primaries, we will return to the client, acknowledge the write. That makes DynamoDB a durable database. So no matter what happens on the backplane, you'll always make sure that if you are acknowledged the write was executed, that the data will be there in the system. Indexes in Dynamo, pretty straightforward. Like almost most databases, you can create indexes on any attribute. And what I'm doing with these indexes, I'm creating alternate views of the data. Right? I'm going to create tables that map the data into different structures. And there's 2 ways to do this in Dynamo. We have a local secondary index and a global secondary index. The local secondary index lets me resort the data. So we talked about the partition key defines a folder or a bucket, and the sort key defines the order of the items within that bucket. If I need to reorder those items within that particular partition, I can use a local secondary index to do that. So think in the case of a customer where we had customer ID and orders sorted by date. Well, maybe I also had another access pattern that says, you know, I need to know the orders by state. I need to know which orders have been delivered, which orders have been back ordered, which orders are pending, right? Well, I might use an LSI for that, and I could, on the LSI, I would create a partition key, which would be the customer ID. And the LSIs always use the same partition key as the table, so it uses the customer ID. But the sort key might be the order state instead of the order date. So now if I want to get orders in the last 24 hours, I'd query the table. If I want to get orders that are back ordered, I would go and query the index, right? So that's an LSI, resort the items within the partition. The GSI is the other alternative. This is to allow you to regroup the data or re-aggregate the items. So maybe on a primary table, I would have, you know, orders by customer by date, but I might have another workflow that says, hey, give me the orders by warehouse by date. So and if I want to do that, then I would create a GSI that would be partitioned on the warehouse ID and sorted on the order date. So I've created a totally different aggregation on that GSI. So that's what we're going to end up using these indexes for. All indexes in DynamoDB allow you to project additional attributes, so I don't have to go back to the table to look up the items to satisfy the access pattern. I can project a subset of the attributes to the index, or I can project all of the attributes to the index, or I can project just the keys of the attribute. So depending on your access pattern, you might only need to know which items actually match a condition. I don't care about the data in those items. And I create a keys-only index for that. Maybe I have an item that has a lot of data, but I have an access pattern that only needs a small amount of that data. In that case, I create an index and project only the attributes I need into that index, and I would do that to cut down the amount of write capacity that gets consumed every time I insert an item, right? Vertically partition the data so I'm reading only the data I need, right? Lots of different use cases for how I might project this data into these indexes, and it really, again, depends on the access pattern requirements of your application. GSIs in DynamoDB are eventually consistent. So when you insert to the table, you're going to be acknowledged the write to the client. It'll kick off an asynchronous process to update those GSIs. Latency on GSI replication is about 10 milliseconds or less. That's the P99 latency. So it's very, very fast. Typically, by the time I insert the data and round trip back to the client, if the client comes back with another request, you're going to get the same data off of the GSI. If I have a highly concurrent access pattern, then maybe that's not going to be a good situation for me. We should talk about something else. But in most use cases, that kind of 10 millisecond latency is quite acceptable. When you look at scaling NoSQL databases, it's really about efficiently modeling your data. And one of the ways that you know that you're not doing it right is when you get things that look like this. This is called a heat map, and we run these for people when they're having problems on their tables. So how many folks have ever, we have a lot of users of Dynamo, how many people are familiar with throttling? Okay, a few of you, okay. So DynamoDB, all NoSQL databases kind of suffer from this disease. If I do not distribute the data well, and my access pattern starts to have a high velocity request against a small section of the key space. What that translates to is a single storage node is delivering all of the load, or handling all of the load of your given application. And that's what this is. If you look at the y-axis, that's the partition count. So there's a number of storage nodes in the table. The x-axis is time, and that red band that's running down the middle means that my application server instances are hammering one little chunk of the key space. There's a high velocity access pattern against a small number of items on the table. That's going to cause this condition in any NoSQL database. Right, so DynamoDB has, in order to efficiently use DynamoDB, the way to be able to do that is to get a large number of storage nodes participating in the access pattern. So that's what a lot of the modeling, when we start to model data in NoSQL, it's about distributing the data evenly across the key space. And that's really what it comes down to. If you want to efficiently use a NoSQL database, you want to manage the partition keys, access to the partition keys using high cardinality values, right? I don't want to use binary values for my partition key. Things like true or false, off or on, in or out, these are bad partition keys because it gives me just a small number of partitions to push all of my data into. What I'd rather see are things like UUIDs, right? Where I'm actually spreading that data out evenly out across the key space. And then I want people to access this data, consistently and evenly over time, right? So tell all your customers to line up and take a number so you can get them through the door in a very even, and orderly manner, like that ever happens, right? So what this really means is we have two dimensions. We have space and time. Space is easy to deal with. We can always lay out the data correctly, and we'll go through a couple examples of how we do that. Time, maybe not so much, right? We have thundering herd type of activities, event-driven workloads. At Amazon, we have Black Friday, Cyber Monday, and Prime Day. This is where people are going to show up, and we know they're coming, and they're going to be coming in big chunks. So that's maybe a little harder to manage, but there are design patterns that we can use to handle that. The reality is if we satisfy those two dimensions, space and time, distribute things evenly, get the access spread out over time, we'll see a much better picture. This example, maybe this table's a little under provisioned. I might tell the customer to dial down the provisioning here because they're not really using a lot of their capacity. But you get the idea. What we really want is to see an even distribution of color in these heat maps, right? We don't want to see big red lines cutting across. All right, getting into data modeling. When you're talking about NoSQL, it's really all about those aggregations. We talked about NoSQL being the technology for OLTP applications. OLTP applications are always trying to group data in the context of one dimension or the other, right? It doesn't really matter what the application is, social networking, IT monitoring, document management. Any type of application you might develop, you're going to be looking up what are all the items that match this dimension or that dimension? What is the one thing that matches this criteria? There's always some sort of aggregation that I'm trying to pull out of the system. And the way we've done that in the past is to use relational database technologies, right? RDBMS. It's been a beautiful technology. It's worked for many years. And so if we look at an example of a product catalog, this is a pretty straightforward normalized data schema. You can see all the typical types of relationships you might expect, a one-to-one between products and books, one-to-many between albums and tracks, and a many-to-many between videos and actors here. And if you think about all the queries that have to be executed to get a list of all my products, right? There's 3 different queries, varying levels of complexity, joining tables across multiple locations in the disk, and you can kind of visualize what the CPU has to do to produce those views. It's got to hop all over the place. It's got to pull data out of multiple tables and create these materialized views and shove them back across the wire, and I got to do it with 3 separate queries. So maybe that's not a really good approach for this particular application. Maybe a better approach is to denormalize that hierarchical data into a collection of items or documents or a collection of items within a single partition, and now it's a very simple access pattern to get all my products. Right? It's one query, select star from products. If I want to get all the books, select star from products where product type equals book. Right? I don't have to go and execute many queries. I don't have to join tables. I don't have to produce these materialized views. And then when I go to update the data, right, if I change one of my product definitions, I don't necessarily have to create a transactional envelope to do that in. Right? All I really need to do is update a single document. So when you actually look at it, ACID transactions come into play mostly because the relational model itself not because of the nature of the data. So a lot of times that's what we end up doing with teams, is working with them to understand how to get your data grouped into a construct that allows you to use an atomic update versus a transactional update, a lot less overhead. So if you look at modeling in DynamoDB, this is applicable to all NoSQL databases. It comes down to two things. We're going to select a partition key and a shard key. Now we call them partition keys in DynamoDB, or a partition key and a sort key. They're partition keys in Dynamo, they're shard keys in MongoDB, again, partition keys in Cassandra. You can think of them all the same. When I say partition key, you can think shard key. When I say sort key, you can think index, right? That's the MongoDB equivalence. I use all of these patterns. It doesn't matter what the NoSQL technology I'm working with, they are all the same. When you talk to people and say, oh, it's a document store, it's a key value store. Look, people, it's NoSQL. And NoSQL is all about matching your data schema to the access pattern. It doesn't matter what the underlying database technology is, it's all the same. So again, with partition keys, we want high cardinality sets, right? I don't like in-out binary, male, female. We like things like device ID, customer ID. Things are generally distributed. With sort keys, it's about modeling those primary access patterns, especially for the primary table schema. What's the primary access pattern for your application? What am I looking to do with this? Is it orders by customer, or is it parts by assembly, or something like this? This is how we're going to actually model that sort key. And then what we're going to do is try and set up the schema to allow us to query across multiple entity types. Right? So when we're looking at retrieving data from the system, I don't want to have to select star from this table, select star from that table. I want to make one query and get all the data back to satisfy that access pattern I need. We'll talk a little bit about what that actually means. But when we get into, and I should probably have my glasses up here, I can't read. So when you get into the tenets of NoSQL data modeling, it really is about understanding the use case. There is no lowest common denominator in NoSQL. Right? In relational database technology, we had this third normal form. You can map everything into the third normal form, and then we'll start talking about how do I construct queries to access the data. Maybe I need to add an index or two to make those queries performant, but I didn't really need to understand every access pattern that was going to be run against the data before I actually created a data model. Right? I could always extend a normalized data model and add a new query. Not so with NoSQL. With NoSQL, if we get it wrong, it can really be painful. It can be an ETL. It can be you might need to restructure the data. So getting it right in the first place is very important. So understanding the use case, identify your access patterns, and model the data to support those access patterns efficiently. And then it's an iterative process, like all development is. Right? It might not be the right model in the first cut. You might go ahead and execute some tests and run some pattern load and find out that that's not actually what you wanted. So we break this down and you say, okay, what is identifying the use case? It's understanding the nature of the application. Is this an OLTP app or an OLAP application? If it's the former, it's probably a good fit. If it's the latter, it's probably not. That's pretty simple and straightforward. Define that entity relationship model. This is a primary kind of process, a fundamental process in building modern applications, is understanding all of the entities in the application, how they're related to each other. And that doesn't go away just because I'm using NoSQL. This is why I say NoSQL is not, I mean, a lot of people describe it as non-relational, but it is not. All the data is relational or we wouldn't care about it, right? I mean, it's just kind of fundamental. If I need to get all the orders for a customer, there's a relationship there. So how do I model that relationship, right? Understanding that entity relationship diagram, and then understanding your data lifecycle requirements, right? What am I doing with this data? Do I need to hold on to it forever? Is it going to cycle out of the system? So on and so forth. Then we get into the next step, which is access patterns, right? Where is the data coming from? How is it being written in the system? How is it being read out of the system? All of these things are going to have an impact in how we actually model the data. There's many ways to do it. And then the last thing we're going to do is actually create a data model where we want to create data structures that allow us to avoid unnecessary queries, right? So a lot of times what I'll see people doing, again, is taking their relational models, moving them into a NoSQL database, and then trying to execute all of those relational queries and managing all of that at the application layer. That's very, very painful. It's not very cost efficient. It's going to actually be a lot more expensive than using an Oracle or an MS SQL. So don't join data at the application tier. Create data models that allow you to use simple access patterns and queries. And then again, it's an iterative process we're going to go through as we build out these models. Okay, let's get into the meat of the discussion here. We'll talk a little bit about design patterns and best practices. The first thing that we want to talk about is Lambda and streams. So streams is the change log for a DynamoDB table. Every write operation that occurs against the table will show up on a DynamoDB stream, and it can trigger a Lambda function. So Lambda is, serverless code. It will execute on the items in the stream. Lambda functions have two roles when they're triggered by the stream. They have an execution role, invocation role and an execution role. So the invocation role is what can it see. So we talked about fine-grained access control. You're going to assign an IAM user to the Lambda functions that are executing on the stream, and based on the privileges that you have assigned to that IAM user, it will see certain items on the stream, or maybe not. It will see certain, it will not be able to read certain attributes within those items, and so on and so forth. Basically, that invocation role defines what can it see. And then the execution role defines what can it do. So what other services within your AWS account space does that Lambda function have access to interact with to be able to process that data? So you can reduce the scope of access on those Lambda functions to access services specifically, only the specific service set that they need to access, and only see the data that you want them to be able to process. Now, what can it do? This example is not all that exciting. It's just taking those attributes and dumping them out to the console, but it's code. Code can do anything, as you know. So, whatever your heart desires, that's what Lambda can do. And people do a lot with it. Probably the first thing and the most important thing that we have people do is table level and item level metrics. So NoSQL databases are not very good at computed aggregations, right? So if I need the thing like a sum, a count, an average, these types of things, NoSQL databases aren't built to compute things on the fly. They're built to do simple selects, right? Gets, not computes. With Lambda, however, we have the makings of an eventually consistent aggregation framework, right? So if you look at MongoDB, they have this thing called aggregation framework. And the first thing the MongoDB SA will tell you is don't use it, please. It's not efficient, right? It's basically, it's like it'll grind through the collection data and it'll produce a result for you, sure, but it's going to chew up the CPU, it's going to be extremely expensive, and it's not going to be very performant. If I'm running a single replica set, it'll work. As soon as you add 2, 3, 4, 5 replica sets, it's going to grind to a halt because all of that data sooner or later has to coalesce into a single place to be able to compute an average or any aggregation, right? So if you look at the aggregation pipeline in MongoDB, they basically split it. There's a distributed portion of it that all of the shards can run, and then there's a certain amount of it that can't be run on all the shards. It has to be run on a single shard, and that's when they send all the data down to one place. So the bigger your collection gets, the less likely you are going to be able to compute those aggregation queries. Now, with Lambda, on the other hand, what we have is the ability to run these things asynchronously. So as I push data onto the table, these updates are going to show up on the stream, and the Lambda functions can actually compute those aggregations and write those aggregations back to the table as metadata items. So now when I need to get a sum or an average or a count of the items that are in my partitions, I can actually just read a metadata item. I don't have to execute that compute query every time and pay that cost. So it's a way to amortize or more efficiently execute those types of aggregation queries. It's a highly scalable, eventually consistent aggregation framework. We use it all the time. This is an excellent design pattern for things like time series data, right? So I'm pushing time series data into partitions on a DynamoDB table, and as I load those partitions, my Lambda functions are running in the background and computing all the averages, the sums, the counts, the max mins, last n, top n, whatever it is you're looking for, and it writes those back into little metadata items in all those time series partitions. Now when I execute my time series computations, all I need to do is read those metadata items and compute a very simple computation at the application tier. I don't have to grind through millions and millions of items on a table and compute those things in real time. That's a heavy cost that you're paying to do that, and we can offload that cost using this pattern. Other things people do: update indexing systems, cloud search, Elasticsearch, third-party technologies, interface with Kinesis, right? You can push the data out to Kinesis fire hose, roll it up, shoot it out to S3 for a backup. It's code, again, you can do anything with it. Interface with third-party systems, anything you want to do. So Lambda is a really powerful stored procedure engine, I guess you'd say, for DynamoDB, right? And one of the nice things about it, how many people have heard about Amazon's migration from Oracle to NoSQL? Okay, yeah, that's, my team actually executed a lot of those migrations. And so we have 384 tier 1 services. We have about 12,000 tier 2 services. A tier 1 service is a revenue generator. When those things are down, we're losing money. And there was a mandate in the company that all tier 1 services had to be deployed on NoSQL technologies. And one of the reasons why was because the impact of a bad stored procedure on multiple services, right? When we have an Oracle instance, I might have 5 or 6 teams using, and somebody pushes a bad stored procedure into that and knocks the processing space sideways, and all of a sudden I've got 5 services going belly up. And so one of the reasons that we decided to get off of that and go to this pattern was because DynamoDB gives us the ability to execute those stored procedures in a disconnected processing space. It does not impact the table's availability. As a matter of fact, I can write very, very bad code in my Lambda functions, and I'm not going to impact anybody's availability, except maybe the availability of the cash in my bank account, but that's okay, because you're writing the check to me. Anyways, okay, so we get into talking about how do we actually model data. Probably the most important thing that we're going to do is leverage a concept we call composite keys, right? So composite keys are a way to be able to model data hierarchically using sort keys, and the way that works is kind of like this. So if I had a table where I had maybe user sessions, and sessions have status, and I'm interested in getting all the user sessions and have a pending status, and I want them ordered by date. So maybe the first take at that would be to create a table where I'm partitioned on the opponent, and then I'm sorted on the date of that game session, and I would say select star from table where the opponent equals Bob. I'm going to sort by date, which is my sort key, so that's great. All the items come back sorted by date. And DynamoDB gives you 2 conditions to be able to filter items on. One is called a sort key condition. That is applied before the read. In this case, there is no sort key condition. I'm just taking the sorted order of the items. The second is called a filter condition. That is applied after the read. So in this case, I might say, okay, give me all the items where opponent equals Bob. They're going to come back ordered by date. I'm going to go ahead and apply the filter condition and say, give me only the ones that are status pending. So in this case, I'm filtering out 1 item. I'm turning back 2. And that's really not really all that painful. But what if there was 10,000 items in this partition, I only had 2 that were status pending? I don't want to read 10,000 items just to return 2. That's a pretty expensive read. So a better way to do that would be to create what we call a composite keys. Composite key would be to take status and date, push those 2 things together, and create a new sort key called status date. And when you look at what that does on the table, it now creates a faceted search. Right? I have items stored within that partition that are sorted by state and date, and I can actually execute a much more selective query and say, give me all the items that start with pending. That's a sort key condition that gets applied before the read, and now I'm only going to read those 2 items. So there could be 10,000 items in that partition, but if I have that composite key structure like that, and I say starts with pending, I'm only going to read the 2 that actually start with pending. If I want to get pending in the last 24 hours, I might say starts, that's between pending under bar date 1 and pending under bar date 2, and use ISO 8601 date strings. Those are string sortable. Now I've got a nice sort key condition that'll give me pending items in the last 24 hours, if that's what I want, right? So nice way to be able to create those kind of composite key views or faceted search indexes using composite keys. So we'll use this technique a lot when we get into actually modeling complex data. And that's what we're going to talk about now when we get into some of the more advanced use cases. And we'll get into some of the examples using Amazon services that we actually re-architected. So the first thing to understand is how do OLTP applications use data? And mostly, again, it's hierarchical views using this kind of, and represented traditionally as this third normal form. They're entity-driven workflows, right? When I code my application, I'm going to have some application layer entity. It's going to be populated with data that lives in multiple tables, and it's the primary driver for ACID is that when I update that application layer entity, I need to make sure all that data goes in consistently. I don't want someone reading and reconstructing that application layer object while it's half updated, right? This is why we create ACID transactions. So generally speaking, 90% of ACID transactions are a result of the fact that we've normalized the data. When you denormalize the data, I don't necessarily need that ACID transaction, but there still are use cases where we do. And one of those use cases might be in version control, right? So in this particular case, let's say I have items, I want version history. Maybe I need to create items in multiple passes and I want to commit them when they're done, right? So in this example, let's say I have a table where I'm partitioned on the item ID and I'm sorted on the version, and the version 0 item is always going to contain a copy of the current item. So if the way the state of this data might look is I'd say, okay, select star from table where item ID equals 1 starts with v0. It's going to give me the most current version because that always is a copy of the current version. And in the v0 item, there'll be some attribute that tells me what version it really is. Then when I create some new version and I'm ready to commit it, I'm going to clobber v0. So in this example, let's say somebody's come along, we created v1. v1 was initially copied onto v0. Somebody else came along, they created v2. They clobbered v0 with a copy of v2. Now I'm creating v3. So v3 is in the partition. We execute multiple transactions against v3. When we're ready to commit v3, we're going to clobber v0 with a copy of v3 and set the current version attribute to 3. Now somebody's going to come along and read v0. They're going to get version 3. So this is a way to be able to kind of maintain consistency when items are going to be created in multiple passes, right? So that could be a good use case for a transactional type of workflow, right? Multi-version concurrency control. The nice thing about this is now then I have the ability to get an audit trail on those items. We use this pattern a lot when we have data where people actually need to know what changed and when did it change and who changed it, right? Because we can put breadcrumbs into these items that'll tell us all kinds of information about who made those changes and what updates were done, right? So this is a really useful pattern when it comes into having to maintain a version history on your items. The other nice thing about this type of pattern, it gives you the same types of views we're very familiar with ACID transactions, like a read committed. Read committed starts with v0. Read uncommitted, scan forward index false, limit 1. It's going to give me the most, currently committed or uncommitted item in the partition if there's any item that's being modified at that time. So that's a very good pattern for that. Hierarchical data. This is an example that we used for a contact manager at Amazon. If you go into our wiki and you pull up office information, somewhere in the system it's hitting this table. This is pretty straightforward, straight linear hierarchy. We've got countries, cities, no glasses on again. What do we got? Country, states, cities, and offices. And the way we designed this table was we put a partition key on the country, and then we created a sort key, which was the state hash city hash office ID. So now when someone comes into the system and says, give me all the offices in New York, we just say starts with, or partition key equals USA starts with NY. Gives me every office in New York. New York State. Give me everything in New York City starts with NY hash NYC. Gives me every office in New York City. Or I could get a specific office by filling out the entire state, city, and office ID. So this is a really neat pattern that lets us create this single table view of this multi-table hierarchy, right, and allows me to be able to select items very easily without having to join data or having to look through multiple tables. Again, we're taking a relational design and we're pushing it into a NoSQL database, but does that make the data non-relational? Of course not. The data is still relational, right? We're just modeling it differently. And when you look at modeling relational data, we talked about the entity relationship diagram. Well, this is a simple example of another internal service we have at Amazon, which is configuration management service. We have resolver groups, we have configuration items, we have contacts. Contacts are associated to resolver groups, so resolver groups own configuration items and they notify contacts. So lots of different access patterns we might have against this particular data set. If we look how we actually model that in DynamoDB on a single table, here's another view of a single table design for contact managers. And so it's pretty straightforward. In this example, we have contact partitions and we have resolver partitions. Resolver partitions we're going to load up with the configuration items that are associated to the resolvers. And the contact partitions is really interesting. We're going to actually denormalize those contacts across the resolver groups. So for every resolver group that the contact belongs to, we're actually going to create a copy of that contact item. We're going to reinsert it into the table with a new sort key. So if you look at this, the contact partitions have a copy of each contact has a copy of itself for each resolver group it belongs to. Now the reason we're going to end up doing this is because we're going to want to create indexes on those. So inside of the resolver group partitions, we'll have some metadata that describes those resolver groups. And again, we're going to load those configuration items into those resolver groups. So we're pushing all of that data that was in that entity relationship diagram, we're pushing it all into a single table. And then what I'll end up with is a couple of views on that table. So if I want to select from the for the resolver group, I can get all the contacts for the resolver group by going to the reverse lookup GSI. Right? I just switch the keys around. So now I'm indexing on the GSI. I've got a partition key. The partition key is actually the sort key of the table, and the sort key of the reverse lookup GSI is the partition key of the table. The other types of access patterns that we might run against this index are, what are all the resolver groups for a configuration item? Right, some configuration items might apply to more than one resolver group. This is part of the workflow. And part of the access pattern they needed was to know what are all the configuration items or what are all the resolver groups for a given configuration item, and what is the status of that configuration item for that resolver group. So that's, again, just can query the GSI by the configuration item ID, and I'll see all the resolver groups it's associated to and what the status is for each one of those configuration item associations, and then of course troll the metadata, for all of the resolver groups, get all the resolver group metadata. So that's neat. That's a pretty small service. Everything we've kind of looked at so far has been relatively straightforward, just a handful of access patterns. But let's talk about something a little more complicated. So there's a theoretical delivery service called Get Me That, right? So Get Me That is, basically we give you the ability to go pick stuff and tell us where to drop it, right? What does that look like from an entity relationship diagram? It's more complex, right? Now we have 5 or 6 different entities. These things all have lots of different attributes. Drivers have a physical location. That physical location might, when we're doing our scheduling, I might need to know, are my drivers available now? What is their status in 5 minutes? What is their status in 10 minutes? So on and so forth, as I'm trying to schedule out my orders. And a lot more complex interactions between the systems. So if you look at the actual access patterns, you get orders by date range, by customer, by vendor, get order details, get deliveries by date range, by driver, right? So we're expanding the number of access patterns here. I mean, this particular example maybe has 8 to 10 access patterns, not just 2 or 3. So a much more complicated type of implementation. If you look at the relational approach, again, we take multiple tables. We could run queries across these tables and start to model this data that way. But if I needed to scale this system, it might not necessarily work so well with relational database. This is one of the reasons why relational databases don't scale, because the CPU overhead that's involved in all of these complex queries. So let's go back to a single table design. In this example, a little bit more complicated, and we're using an approach that's going to allow, again, we want that primary table to give us to satisfy our primary lookup pattern. So what are the patterns? Well, I'm going to look up maybe customers by email. So that might be the first lookup here. Say, okay, I'll use a partition key for my customer partitions. I'm going to use their email, because really IDs don't help me. When someone calls the call center and says, oh, I need some help, you don't ask them, well, what's your customer ID? Right? You ask them, what's your name? What's your email? Right? So the access pattern more often is not to look things up by the ID, but to look things up by some attribute of the item. So use those attributes as your partition keys. In this example, we'll use partition keys for the drivers, and for the customers, it's going to be their emails. If in a customer situation, select the customer metadata. What's your email? Sort key equals customer. That gives me your customer metadata. And maybe I want the orders by customer by date. In this particular case, I'm going to put the orders for each customer. We're going to use those partitioned on the customer's email and sorted on the order date. So if I execute a query against a table and says, give me all the orders for customer in the last 24 hours, I'd say, give me all the orders associated with this email with a date range greater than 24 hours ago, right? That's going to give me the orders for a customer. If I want to get vendor information, I'll use the vendor ID, right? Now this is a use case where the vendor ID actually makes sense because, you know, I might have multiple stores, a franchisee might be operating, a single email might be associated with multiple stores, so you'd want each one of those stores to have a unique ID. Maybe email doesn't work for vendors. So I'd select star from the table where the vendor ID equals X. I'll get the vendor information. Drivers, I can get driver status using email and the sort key equals driver. In our particular use case, I want drivers' positions in 5 minutes, 10 minutes, and current. So I could go ahead and create their GPS information, their estimated positions in 5 or 10 minutes from now, store that all in the drivers' partitions, and so on and so forth. Insert the items on the table, and so on. Now, the important thing to understand when you're looking at DynamoDB is that there's a 5 GSI limit, right, to the table. So a lot of times people will say, well, I can't use DynamoDB because it only has 5 GSIs. Well, those GSIs can be overloaded. So in this particular example, what we're going to show you is how the order items might have a GSI1 PK that is the order ID and a GSI sort key for GSI1, which is the email of the customer. But other items on the table might have different values in those GSI keys, right? So in this particular case, customers and drivers' GPS information is going to be going into the GSI1 by grid. It's not going to be going in by order ID. So I have a whole different sets of items that I'm storing on these indexes based on different attributes and different values of those attributes. The items are actually going to be indexed by completely different dimensions. They will also be indexed by order ID on GSI1, but they'll be indexed by driver emails as a partition key on GSI2. So what does this do to the indexes? When I look at the indexes, I'm going to have actually multiple access patterns I'm executing against each one of these indexes. So in this example, I've got, let's say I want all the items for an order. I could just select star from GSI1 where the order ID equals X. It'll give me all the items for the order and all the customer information for that order. This is a key in NoSQL modeling. I don't want to query twice to get the customer information and the order information. When I have an order ID, I'm going to want to know who ordered it and what items did they order. I don't want to have to query the database twice. I want to query it once. So what I'll do is create an index that indexes both the customer items and the order items into the same partition. And that's what we've done here. So now when I select off the index where order ID equals X, I'm going to get not only the items that were in the order, I'm going to get the customer's information for that order as well. Single query. It's a lower latency experience for the customer. If I want to get drivers information, right, maybe I need to know, hey, what drivers are available in grid X 5 minutes from now? Okay, now what I've done is I've taken all the driver's GPS information and I've sorted it out by grid onto this GSI. So maybe I have a vendor that's ready for an order to be picked up. It's gonna allow me to do that. GSI2 then is going to give me the ability to query on a different set of dimensions. The key information here that you should take away is that we're going to overload these indexes to satisfy multiple access patterns. So the 5 GSI limit is really irrelevant because I'll use those GSIs multiple times over and over and over again. All right, so I'm out of time. I've got more models here to show you, but I don't have any more time to show them to you. So I'm just going to go ahead and leave you with one more little thing that we'll talk about. This is the serverless ecosystem in DynamoDB. This application was a little app that we wrote for the AWS Solutions Architecture team. They were looking for anytime feedback from our customers. So how many people have interacted with an SA and seen a little, you know, do you have on your signature, do you have the rate my interaction link? Yes, that's this app. You can thank me. So we wrote this application because we wanted users, our customers, to be able to tell us how well we were doing, and they actually tell us a lot how well we're doing, which is really cool. But it's a very straightforward app. We have some HTML form that sits in the S3 bucket. When you click the link in the email, you're going to pull down that form. It's going to take a look at it. You hit post, it goes up to API Gateway, runs a little Lambda function. When we wrote the app, we didn't have encryption at rest, so we had to take personal identifiable information and push it in the S3 bucket. We put the rest of the searchable metadata into DynamoDB and sent it off to a notification off to the manager. The important thing to note about this application is it costs us nothing to host this, literally nothing. I got one HTML form in an S3 bucket. The DynamoDB table's in the free tier, but if I had 1 million users show up tomorrow, all I have to do, we have auto scaling up on the DynamoDB table, It's just going to scale the capacity and satisfy that load without me having to deploy anything. And that's the power of serverless. We wrote this application in a week. We deployed it. It cost us absolutely nothing. If 1 million users showed up tomorrow, the system's going to automatically scale to support it, and I don't have to do anything. There's no other infrastructure in the world that allows you to operate that way. So when you talk about being able to fail fast and fail cheap, right? This is an excellent way to be able to push things out there. You don't know whether they're going to succeed, but you don't have to pay through the nose to get them out there for people to use. And that's what's really cool about serverless. Anyways, conclusions, NoSQL does not mean non-relational. Absolutely does not mean that. The ERD still matters. RDBMS is not deprecated by NoSQL. They've still got a great set of use cases for it. What we really want to do is use NoSQL for OLTP or decision support systems or data warehousing at scale. That's the sweet spot. Anything else, you're probably using either too big a tool for the job or you're using the wrong tool for the job. If you're using RDBMS, it should be for OLAP or OLTP when scale is really not all that important. Okay, and so that's kind of your takeaways today. I hope you got something out of the session. Thank you so much for staying all this time and listening to me.